So good morning. Thanks for joining me. My name is Maria Colgan, and in this morning's session what I'm going to do is go over the different aspects of the execution plan, lead you through exactly what the different options are for each section so that you get a much better understanding of why the optimizer is coming up with the execution plan it is, and it will hopefully prevent you trying to force a plan that isn't possible for the optimizer. So I know we all want an index unique scan, but it isn't always possible. So I want to go through with you all the things that control the decisions the optimizer makes to make it a little easier first for you to read the plan, and then second to understand why the optimizer has come up with that particular plan. So we're going to start with what is the plan, then I'm going to jump into quickly how to generate an execution plan, and then we'll get into the nitty-gritty of the different components within the execution plan and how the optimizer comes up with those. During the course of the session, you are going to be required to be the optimizer. You're going to take on that role. We're going to look at some queries. You're going to tell me what execution plan you're going to come up with. So audience participation is required. So I hope you had that second cup of coffee at breakfast. If you didn't, you're going to regret it now, but that's okay. Once we understand the execution plan and the different components, we are going to evaluate one last execution plan together. You're going to see this plan throughout the presentation, and at the end I'm hoping to have you tell me whether or not it's a good execution plan, and if, as the optimizer, you would change that plan at all. All right, so let's get going. What is the execution plan? It is basically a set of operations that, or steps that are necessary to execute or complete your query. Now, each step or operation is either going to produce rows or consume rows. And there's even some operations that will do both. They'll consume rows from a previous step in the execution plan. They'll process them, for example, perhaps they join them, and then they'll produce a set of rows as well. But it's basically a flow of rows through different operations until we complete your SQL statement. Now, it's typically seen as a table. But actually, if you go into an optimizer developer's office, they never draw the execution plan as a table. This is what we normally see, right? When we use the different tools to view the plan, they'll always draw it as a tree, with each step producing or consuming rows, and the rows kind of flowing up through the tree. We always start typically on the lower left-hand side of the tree. That would be the first table that's accessed. Those rows would flow into the hash join. Now, the hash join can't do anything with just one set of rows. It needs two to complete the join. So then we'd come down, we'd access sales. Then we'd send those rows into the hash join, which would complete the join and produce rows that would go into the group by. Does that make sense? So it's typically a tree. I'm not expecting you to suddenly start drawing all of your plans as trees, but it can help you mentally visualize what's going on if you see it as a tree. There are a number of tools that will show you the execution plan as a tree. So SQL Developer can do it, and what is the other one I'm trying to talk about? We don't talk about that one. What was the one you were showing in yours? SQL Monitor. Thank you, finally, eventually gets to me. SQL Monitor and SQL Developer will show it to you as a tree, and potentially that other one that shall not be mentioned also. So, how do we generate these plans? There are a bunch of tools out there to view a plan, but they don't actually generate the plan. So you can view a plan in Auto Trace. You can view a plan in SQL Monitor. That was the one I couldn't remember. How many folks are using SQL Monitor today? I'm hoping to convince a few more of you by the end of it. For those that didn't raise their hand, is it because you don't own the diag and tuning pack? Is that why you don't use it? I use Method. Oh gosh, okay. You aside, why don't you guys use SQL Monitor? You use Toad? Is that what I heard? Lord of mercy. Okay, I may never win that one. All right. So SQL Monitor, to me, is the best one out there, and it is visible through SQL Developer and also through TK Prof. But there are actually only two ways to generate a plan. So there's loads of different ways to view it, including that animal that you keep shouting at me. But there's only two ways to generate it. And each of those tools will use one of those two methods. The first method is to use the explain plan command. The explain plan command is not actually going to execute the query. It's going to parse the SQL statement and come up with the execution plan, but not actually execute it. The second option is via $SQL plan. Here we're actually executing the SQL statement and storing the execution plan in a dictionary view that showed up around in Oracle 9i. And as I said, it's the actual plan that's in the cursor in the shared pool, so the one that actually got used during execution. Now, why am I making such a big distinction between explain plan, where we don't execute, and $SQL plan, where we do? Because the plans may not always be the same. Anybody think of a reason why the plan between explain plan and $SQL plan would be different? Something in the buffer cache? It's the binds, actually. Bind values. So if you've been following Tom Kite and all these folks who beat you up and say, please use binds in your SQL statements instead of literal values, so that we can take the pressure off the shared pool and be more efficient in the database, then you're going to be in a little bit of trouble if you do explain plan. Because explain plan, because it's not executing the statement, doesn't bother to peep at the bind value. So it doesn't know what those bind values are. So it assumes uniform distribution. So histograms aren't taken into consideration. A bunch of things are not done. So if you've got literal values in all of your queries, perhaps you're in a data warehouse or a very ad hoc environment and you don't use binds, then you'll probably see the same plan in both cases. If you do have binds, you may not see the same execution plan, and I would strongly recommend you look at $SQL plan. So let's talk a little bit about how you do that. They're both going to use, in order to see or display the plan, you're going to use the same PL SQL package. It's called DBMS XPlan, but you're going to use different procedures or functions within that. So with explain plan, you want to use the display procedure in DBMS XPlan. And it takes 3 arguments. We'll explain what they are in just a second, but it's going to show you the output from that explain plan. If, on the other hand, you actually want to see the execution plan used for a given SQL statement, you're going to want to use DBMS XPlan display cursor. Again, it takes 3 arguments, and I'll explain what they are in just a second. But if you let them all default, so that the first 2 are null and the third is basic, what you'll actually get when you execute that command is the explain plan or the execution plan for the previous statement in the session. So by default, it spits out what was the execution plan for the last SQL statement in this session. So what parameters do I need to pass to these? By default, I never pass these guys any parameters. I typically just run an explain plan followed by DBMS XPlan display, or I run my query followed by DBMS XPlan display cursor. But if you do want to be very specific about it, for display, you've got to give me the plan table. You can give me a statement ID, and you can give me a specific format that you're interested in. And I'll talk about formats in just a second. If you're doing it through display cursor, it also takes 3 parameters. You need the SQL ID, the child number. Now, why would I have multiple children? The stage whispering on the far side of the room is because you've got bind variables, and if you're peeking those binds, we may actually come up with different execution plans for the different bind variables. Started in 11G, this ability to have different plans for different bind variables. So you may have multiple children. By default, it's 0, which is the first one, but if you've got multiple execution plans for a given SQL statement, you might want to look at different child numbers. How do I know how many children I have? $SQL will tell you how many children you have for our child plans you have for a statement. And then again, the format. Now, when we look through this session, you're going to see a bunch of different execution plans. You'll see them in slightly different formats, and that's what that final parameter is going to control. Basic is the typical one that you see. Then you can do typical, you can do all, and I'm going to show you some tricks of some additional parameters you can pass to get more information as we go through the presentation. There is a great blog on the Optimizer blog, super easy to remember, blogs.oracle.com/optimizer. Okay? If you go there and you just search for Explain Plan, you'll get a great blog on the formatting of the plans and how you can get extra information out. But I will show you that as we go along so that you guys can kind of see some of those hints as well. Before we get into the actual plans, I just want to spend a couple of minutes talking about what the Optimizer considers to be a good plan. I know we may differ in our opinion from the Optimizer from time to time, but I want you to just get an idea of what it's after. And the Optimizer actually has two different objectives depending on how you're executing your queries. If you execute your queries serially, so a single process is involved in executing that query, the Optimizer is all about cost. It is looking to find the plan with the lowest cost. And the mental mindset is the cheaper the better. If, on the other hand, you're running a query using parallel execution, so you're starting multiple processes to execute that query, then the Optimizer's goal is all about performance. The faster, the better. How can I execute this query as fast as possible? Now, I certainly know when I sat on your side of the room, the first thing when I was told both of those rules was what's cost and what's performance. What does that actually mean? So let's take a little bit of time to look at what is cost. Cost has been accused of being many things, right? A magical number that the Optimizer just makes up to piss us off. That's a strong contender. The resources required to execute the SQL statement, or an estimate about how long it takes to run the statement. What do you guys think it is? Yeah, it's number 2. The actual definition is the cost represents the amount of work required that we believe is required to complete the SQL statement. And that work is measured in system resources. So CPU, I/O, and memory are taken into consideration when we're looking for that. So we're looking for a SQL statement when we're executing serially that will use the least amount of CPU, I/O, and memory. It is an internal calculation. I wouldn't waste my breath or time trying to teach you how to come up with the cost. It is there really only to allow you to compare two execution plans. So don't worry about where the numbers come from. We only use it for comparison purposes. I'm not going to waste your time in how they come up with it. But you should be aware that we are looking for the plan with the lowest cost. So if you've come up with your magical plan and we say that it's going to cost $10,000, don't be disappointed if the Optimizer says, I'm going to go with a different plan that only costs 10. See what I'm saying? It's always going to favor that one with the lowest cost. For performance, let's see what it might be. Getting as many queries completed as possible, getting the fastest possible elapsed time with the fewest resources, or getting the best concurrency rate, the best number of queries going at the same time. It's the fastest possible response time for a query. So I kind of lied. None of the ones above are quite correct. It is just the fastest possible elapsed time for that query. When you start parallel execution, you're telling the database, or at least it assumes you're telling it, you want to throw all the goodies you've got at this query and get it done as fast as possible. You're not worried about concurrency. You're not worried about anybody else. This one session can have the entire box if it wishes to execute this one query. That's what you're telling us when you give us parallel execution. So that is our primary goal, is to get it done as fast as possible. And we don't really care about how much system resources it takes to do that. Okay. You thought this was going to be about plans, right? So let's get on to looking at some plans. What I'm going to do is I'm going to show you the 4 key elements that make up an execution plan. We're going to go through each one of them in turn. We'll explain what they mean and what potential values you can see for those. I am going to, just in the interest of time, if I had 90-minute session, I would have actually had 2 additional aspects here: parallel execution and partitioning, how they show up in the plan. Given we've only got an hour, I'm going to skip those because not everybody in the room uses them. How many folks are using parallel execution? Okay, so there will be a few nuggets in here for you, but not as much as I would normally have. How many folks are using partitioning? Okay, so if we've got time at the end, I'll show you how both of those kick in. But for now, let's concentrate on the 4 that everybody has, no matter what. And we're going to start with the most important one. How many of you guys were here with me on Sunday when we talked a little bit about cardinality? So some of this is going to be a nice recap for you, but it's going to allow everybody else to catch up with us. The most important aspect of an execution plan is the cardinality. And the cardinality is the estimated number of rows the optimizer believes will be produced from each of the operations in the execution plan. Remember, each operation either produces or consumes rows, or both. And it's that decision about how many rows the optimizer thinks that operation is going to need or is going to produce is critical. And it uses a bunch of the statistics we gather and formulas to determine that value. Okay, here's a quick example. If I've got select star from the sales table where the store ID is 5, and I've got 100 rows in the sales table, and there are 10 distinct values in the store ID column, then the cardinality estimate for that query will end up being 10 rows. 10 rows will be returned. Why? Because the optimizer takes the total number of rows in the table, divides it by the number of distinct values in that column, and that's the estimate it comes up with. Okay? Now, the more complicated the predicates are in your query, the more complicated the formula becomes, but that's the standard approach about how it comes up with these guesses or estimates. Now, the question becomes, why should I care? You care because that cardinality estimate influences all of the decisions that are made in the execution plan. Everything from how we're going to get the data out of the tables, to how we do the joins, to the join order that we take, and the method we're going to use to do any aggregation or group by that you have in your query. So it's very, very important. Here's your execution plan. Where's the cardinality estimate? Yeah, it's in a column called rows. So how do I know if those cardinality estimates are any good? You can compare them with the actual. How do I get the actual number of rows? If you look over here in the ID column, you start to see little asterisks or stars next to some of the lines. If you look underneath the execution plan, it will show you what part of the query was used to generate or is going to be processed in that step of the plan. So for example, on line 6, we did a table access full of department. And the reason we estimated 1 row was because there was a filter predicate on department that said the department name was sales. Let's hope we only have 1 department whose name is sales, but if we wanted to work it out for sure, we could simply do a select count star from department and apply that where clause predicate. That would allow us to test whether or not there really is only 1 department with the name sales. If you don't want to break it down 1 line at a time in the plan and do a bunch of select count stars, you can add a hint to the SQL statement that is called gather plan statistics. Now, contrary to what you may believe, hints are not just there to force a particular execution plan. There are actually 2 types of hints that we have in the database. Those that influence the execution plan, the different steps, but also those that do other things. So it is actually a mechanism we have in the database, and it's used by a number of different teams, not just by the optimizer group, to force the database to do stuff for us. And one of the things we can get it to do is to gather additional statistics. And I'll let you in a little secret. We actually always gather these stats. We just don't normally show them to you. So this information is normally in the cursor anyway, the number of rows that were returned by each of the operations. So if you want us to show them to you and persist them in the plan table, then you need to gather plan statistics hint, and then when you're down here displaying it, you need to change the format from the default, which is basic, to all stats last. Show me the execution stats for the last process that executed this cursor. What will that do? Instead of having a rows column We'll now get two additional columns in the plan display. We'll get an E rows, the estimated number of rows, and we'll get an A rows, which is the actual number of rows returned for each operation for the last execution. Yes, sir?
If you put that hint in and you look at the plan as SQL Developer, is it going to change what you see?
If I'm in SQL Developer and I've got gather plan stats, if I put in the plan, gather plan, do I get an A rows?
We always show actual rows.
I thought so, right? So you don't need the hint to do it.
But it depends how you're looking at the plan.
Yeah, there's two ways to look at the plan in SQL Developer. If I just run, I thought if I just
Auto trace would show
the actuals, but the other, if I just hit explain, I don't think it does because it's doing explain plan. Yeah, so it doesn't work if you do explain plan. You have to execute the query. So as Jeff said, if you're in SQL Developer and you use the auto trace, it'll show you the execution plan and it will show you the actuals. It's as if you've got the gather plan stats in there. If you're using the other animal, I don't know what it does, but I'm assuming if you put in the gather plan stats, it will show you the actual rows. I know if you use SQL Plus or the command line, if you do add the hint and then do format all stats last, you'll get this A rows and E rows. If you use my favorite tool, SQL Monitor, it always shows you both because it gets its information directly from the cursor, all right? So it always shows you both. Now, be a little bit careful. Those of you using parallel execution, be a little careful with this. Take a look at my query. I ran the query with using parallel execution. I did all stats last, but only 2 rows in the plan seem to have information about the actual number of rows returned. Why is that? Which process is the last one to execute in parallel execution? The query coordinator, the guy who writes his name in the plan. The query coordinator, by the way, I always think is like management, right? Superman overhead, tells you exactly what to do, hangs around doing nothing during the course of the execution, and then right at the very end, gathers up all the rows and returns them as if he had done all the work himself. Sound familiar? Yeah. So PX coordinator was the last guy to actually run the cursor because he gathered up the results and he returned them to the end user. So if you're using parallel execution, all stats last is not actually going to be your friend. You're going to want to use all stats all. Give me all of the statistics for all of the folks that executed this cursor. However, if the statement is run multiple times, your all rows is going to be off because it will be an aggregation of all of the processes who have ever executed the query or the cursor. Do you see what I'm trying to say? So if you've executed it multiple times, you'll get some very funky numbers in all rows, which is why if you're using parallel execution, I strongly recommend you use SQL Monitor. Why? Because A, it always shows me the actual rows, and B, it gets it right for each individual execution, even if I'm using parallel query. So just something to think about. All right, so we looked at all of these issues on Sunday, so I'm not going to get into it, but here's some of the reasons why you may not get the cardinality estimate that you want. It could be that you're missing some stats. Easy solution, please gather stats, you lazy bums, right? There could be a data skew in your columns. That means some values are way more popular than others. The optimizer, as I showed you earlier on, assumes an even distribution of rows among all the values. Remember, the default cardinality estimate is total number of rows divided by the number of distinct values. The optimizer assumes there's an even distribution of values in the column. If there isn't, you should think about creating a histogram. Don't be trying to confuse the optimizer by, with all of these additional single column predicates. It assumes every time you add a new where clause predicate to the query, it will reduce the number of rows being returned. Now, again, if you listened to Tom Kite or some of the other SQL performance experts, they'll tell you, be as selective as you possibly can, right? Tell us everything you can to reduce the number of rows. But you know more information about your data than the optimizer does. The optimizer is very optimistic. It assumes every time you give us an additional where clause predicate, the number of rows being returned by the query will shrink because you're being very selective, you're being very explicit. If that's not the case, for example, state and country are being used as two predicates. So I want all of the sales we had in the state of Texas in the United States. Well, lucky for us, there's only one Texas in the world, right? And it's right here in the United States. So adding the additional predicate does not reduce the number of rows being returned. If you've got that kind of scenario in your workload, and you developers, by the way, don't be sitting back thinking that's the DBA's job. You probably know the data better than the DBAs do about what the relationships are. So if you know you've got this situation, you want to start thinking about creating extended statistics and telling the DBAs what columns you're using and potentially what extended stats they may need. If you're busy wrapping functions around columns, you are single-handedly blinding the optimizer. So if you love to put an upper around a column, when you're doing your comparisons, or if you use a lot of NLS or you use other functions, that effectively blinds the optimizer. And so you have a couple of options to help it out. In an older version of the Oracle database, you could create a function-based index to be able to help the optimizer understand what the function does to the values in that column. If you're on a newer version, 11G or higher, you can create extended statistics to tell the optimizer what that function is doing to the values in the column. Same is true for joins. The more columns you use in a join, the more selective we believe that join is going to be. If that's not the case, if for some reason you've got a very complicated data model and you need to join on like 6 columns between the two tables, but the additional columns are not actually that selective, please create those join or extended statistics on both sides of the join so that we can get a much better estimate. And finally, if you've got super complicated expressions, you might want to take advantage of dynamic sampling. What that's going to do is take a small number of blocks from the table during the parse of the SQL statement, apply your crazy expression to them, get a cardinality estimate, and then extrapolate that for the whole table. So there's some of the solutions if you get the cardinality estimate wrong. And as I said, that's the first place to look in the plan. If it's wrong, and the one thing I would look for most is the number 1 in the cardinality column. If you get a 1, and the operation isn't index unique scan, I would be nervous. Why? Because the optimizer developers, although they're super optimistic, they don't like the number 0. But if they get an estimate where they think, haha, there is absolutely no rows coming back, they get optimistic about the plan and they can do some crazy stuff. If you see a 1 in the plan, what that could be hiding is an estimate of 0 rows. They never show 0 in the plan. They'll always round it up to 1. And if it's not an index unique scan and you have 1 row being returned and it's not a unique column that you've put an equality predicate on, take a look at what's going on with your stats and your queries, because that would make me nervous. Okay? If I'm one last thing on cardinality. If I'm looking at the cardinality estimate and I'm looking at the actual number of rows, as long as they're the same order of magnitude, we're good to go. Don't, fret over the fact that there's really only 20 rows returned and the optimizer said there was going to be 21. Don't freak out about that. But freak out if you know there's only 20 rows being returned and the optimizer says there's going to be 20 million, right? So that's what I'm saying. It has to be, if it's the same order of magnitude, you're good to go. All right, access paths. How do we get to the data? How many access paths does the optimizer have at its disposal? How many different ways do we have to get to the data? That's a join method. We're getting there, not that. So how do I get to the data first, though? Full table scan? Yeah, what else have I got? Give me a number. How many people think there's 20 access methods in the database? No commitment to 20. Do we think it's higher? Lower. Look, God, you guys need to get in your game show mode. This is going to get more exciting as we go along. It is lower. How much lower? 10 access methods. Higher? Lower. Lower? Going lower. How many people think there's 9? Yes, 9 there is. 9 there is. So let's talk now. You can break them down into 2 if you really were going to get nasty with me. You could say there's full table scan and some kind of index access. So you could have broken it down into just those 2. But in terms of what appears in the execution plan, there's 9. Let's start with the easiest one, full table scan. Full table scan means I'm going to read all of the rows from the table. I'm going to apply the where clause predicates, try and filter out any of the rows that are not necessary. And it's typically used if there's no index available to help me, or if you've cranked up the parallel degree and we believe it's cheaper to read all of the rows because we've got lots of processes available to help us do it. Full table scan. Not as much the spawn of the devil as most people think. If you've got a good I/O subsystem and you're on something like an Exadata, full table scan is actually quite a reasonable execution plan. But for a lot of people, quite fearful. They're looking for an index. Next up, table access by row ID. What's a row ID? A unique identifier for the row. Somebody learned their book off by heart. Well done. That is indeed correctly identified. It actually tells me the data file, the data block, and where the row is within that database block. It is a unique identifier. Table access by row ID typically comes if I'm getting the row IDs out of an index. So I did an index range scan or something that gave me the row IDs, and then I looked up that information in the table. It can also come if you've got some fancy pants developer who's given you a row ID in the where clause predicate, but typically more likely coming from an index. Whew. Okay, so that's our table access ones. Let's move on to index accesses, right? There's 7 of those. Index unique scan, one of the most beloved access methods, but much harder to show up in the plan than you think. When do we get an index unique scan? Exactly. You have to have a unique index to get an index unique scan. So that's either a primary key or an index on a column that's been marked unique. And it guarantees that only one row is coming back if it's got an equality predicate. Okay, so if I've got an equality predicate on a primary key or a unique index, then I get an index unique scan. Loads of people seem to want it, but they don't seem to realize that there are very strict considerations on when it's going to be used. What's much more common in your plans are index range scans. An index range scan is selected if I've got a non-unique index and I get an equality predicate. What it tells me is I'll navigate through the index looking for the first leaf block that has the data that I want, and then I'll begin scanning from there towards the end to pick up all the values that I'm interested in. The next up, and I'll also, by the way, get an index range scan if I've got a unique index, but I don't have an equality predicate. So if I have select star from sales where the primary key is greater than 5, I don't get an index unique scan, I get an index range scan, okay? Index skip scan, not as commonly seen, but this depends on how well you are at building your indexes. If you put a very unselective or non-unique column at the beginning of your index, but the second column in the index is super selective, you might get an index skip scan. What it means is we skip over the first column in the index and we actually use the second column to drive the access because that second column is very, very selective. You have to really stuff up your index creations in order for that to go on, but it has been known to happen. The next 2, the names are very confusing. You can do a full index scan and a fast full index scan. So let's start with a full index scan. A full index scan does not, in fact, read all of the blocks in the index, even though that's what the name somewhat implies. It actually navigates through the branch blocks in the index to find the first leaf block, and then it scans all of the leaf blocks from there through to the end. It's typically done if all of the columns we need for the query are present in the index, or if there's an order by and the columns in the index are in that correct order. A fast full scan, on the other hand, does read every single block in the index, and it's done typically in replace of a full table scan. So all of the columns I need for the query are here, and I'm just going to brute force read through everything in the index. Typically done if there's parallel query on the index as well, or if multi-block read count has been set very, very high, fast full index scan tends to pop up. One that's less common is something called an index join. An index join is where you may have a very wide table, and multiple indexes on that table have all of the columns that we need for the query. What the optimizer can do is scan both of those indexes and use a hash join to join the results together in order to answer your query. Typically, again, done if you've got a very wide table or a very large table, and you're only going after a smallish set of columns, and those columns are present in those indexes. And then bitmap indexes. How many folks are using bitmap indexes? A couple, typically more common in a data warehouse or data mart environment. They're typically created, or they're best created, on columns that have low cardinalities or a low number of distinct values, things like marital status, or it could be gender, or things like that, where there's fewer values. Because what they do is, instead of storing the individual values, they set bits to be on and off. That's why it's a bitmap. And it can be very effective for us if we've got multiple bitmap indexes. We can do and or operations on those bitmaps in order to be able to produce a set of row IDs from a table. So they can be quite powerful when they're used in conjunction together. But they effectively compress the size of the index quite nicely. All right, back to your execution plan. Where does it show me the access methods? Yeah. In the operations columns, they are my access methods. They show up there in the operations for each of the objects. Now, what if I've got the wrong access method? What would be the first thing you do? Is that add a hint? Or? Look at the cardinality. You go back to step number 1. Check the cardinality estimates that may be, check the stats as well, right? That there might be something wrong with your stats. Let's play who wants to be the optimizer, okay? Now you know what your access methods are. You realize the optimizer doesn't actually have as many choices as you thought, right? He's only got 9 ways to get to the data. You're gonna get a chance to be the optimizer. You've got a table countries. It's got 10,000 rows, and it has a primary key on the country ID. Here's your query. Select the country ID, the name from countries, where the country ID is in AU, FR, or IE. How are you going after the data? All right, let's show of hands. How many folks index range scan? That seemed to be the one I heard the most often. Most of the room. Anybody else? Nobody else? Index unique scan. What? Didn't you say I only got those if there's an equality predicate? You liar. I'm not a liar, but what we didn't really focus on, and I should have really said it at the very beginning, the optimizer does its best to rewrite your query for you. I should have made that more clear perhaps at the beginning. They're a very nice bunch of people, but they're also very smart, and they always think that they can write the query better than you can. And when you come in with an in list like that, they turn it into a series of equalities. Country ID equals AU, or country ID equals FR, or country ID equals IE. By turning them into an equality, it gets to do the index unique scan. All right, I'm feeling bad that I kind of tricked you on that one. Yeah?
So in general, is that more efficient?
Yeah, it's typically much more efficient to do in it, because we just get one row, we go straight into the index, we get it, and we come back out. I feel bad, so I'm going to give you another one. All right, same table, countries, contains 10,000 rows, has a primary key on country ID, Now the where clause predicate is country ID between AU and IE. How many folks are voting with your colleague at the back of the room, index range? How many of you think I'm sneaky and it's going to be an index unique scan again? Your colleague was indeed correct. You should have gone with the man, voted with, right? Index range scan this time. Why? Because we cannot rewrite a between into an equality, so we got to go with a range scan, even though it's a unique index. Everybody's with me so far? You're getting another go. Same table, country. This time it's where the name is equal to the USA. What are we doing?
If we don't have additional.
All right, so there's been a couple of options. How many people still thinks we're going to do something funky with an index? Ooh.
Maybe index scan?
Maybe, yeah, potentially. So 2. How many people are voting with my loudmouths on this side who said full table scan? A lot of non-voters, just saying. Okay. My loudmouth friends on this side of the room were indeed correct. Table access full. Why? Because there was no additional index on the table, as you said, right? That was our only option. When we've got no other options, that will be the fallback plan, okay? Just so you're aware of it. Why would it go wrong? Why would I get the wrong join method? I use a table scan instead of an index. Typically, this is done if either there's something wrong with the index, that it's been marked unusable. It can happen as well if somebody's put a really high parallel degree on the table, making it look cheaper. It can also happen if the value for multi-block read count somehow has been set super high, skewing us towards an index axis. The optimizer picked the wrong index. That's probably the number one email that I get. Your stupid optimizer picked the wrong index. And somehow it's always my optimizer when it goes wrong. There's a couple of things that can trigger this to happen. Statistics will be the first place that I go. Are you missing stats or do you have stale statistics? It's possible that the cost of a full index axis is cheaper than going to an index and then having to go back to the table. The optimizer will always favor an index that's got all of the columns I need. Now, you may have been dumb enough to put it in the wrong order, that it's less selective, but that's not my problem, folks. If it's got all the columns we need, we are going to look very favorably on it. So be very careful about how you lay out your columns and the order in which you do it. You want to put the most selective columns up front, the ones that will help eliminate as many rows or entries as possible. Yes?
Is there a diminishing returns depending on how many columns I have in my index? Say I've got 10 columns in my index. Is it not going to look at my number 8 that often, or?
Yeah, there is diminishing returns. You can get carried away. At some point, if you make the index as big as the table, even though you're just putting the columns in order, it's not going to be all that beneficial. We may end up just going to the table. But it's more if I'm kind of, let's say we've got 100 columns in the table, and I've got an index that's got 3 columns in it, that's in the right order. But it would require me to do an index access table access by row ID, and I have another one that's got all 4 columns that I want. And even though it's not in the right order, we'll pick the one with the 4 columns because it's going to be fewer database blocks most likely to access that entire index. Does that kind of make sense? But yeah, you will get diminishing returns. You can't, just keep adding columns. At some point, you've got the table again. So that typically tends to be what's going on. All right, just in the interest of time, I think we have only 15 more minutes, so I'm going to jump on to join methods. Now, we had 9 access paths. How many join methods do we have? 4. Ooh, that seemed very confident. Where was 4? All right, 4. What are the 4? Oh, goodness. Inner, outer. So they are join types. They are not join methods. But they are correct. They are very correct that he said there were 4 join types, which was inner, outer, equality, and non-equality joins, which are join types. But join methods. How can we do the join? Hash is one. Cartesian is a type, actually. Nested loop and merge sort. So how many do we've got? 3. We have 3 join methods. Nested loops. For you developers, this should be one that makes perfect sense to you, as it's 2 for loops, right? For every row in my outer loop, I'm going to go through every row in the inner loop. It's like 2 for loops, right? That's how a nested loops join works. For every row in the outer table, I'm going to scan through all of the inner table or the inner loop to see if I've got a match. Typically done if I've got a smaller table that can be on the inside of the loop, or I have an easy mechanism to look up the rows. For example, I have an index that will, on the join column, that will allow me to probe into that table. That's a nested loops join. Hash join is, by the way, nested loops is typically done if the tables are small, if we think the tables are small. Again, your stats are important here to tell us that the tables are small. Hash join, a little bit more complicated. We start always with the smaller of the 2 tables. We scan that table, we apply any where clause predicates we have, and based on the results of that scan, we build a hash table in memory by applying a hash function to the join column. We then go over and we scan the second table, apply any where clause predicates we have to that table, and then we apply the same hash function to the join columns from those resulting rows, and we probe into the hash table to see if we've got a match. Any matches, that row gets returned. If there's no match, the row is disregarded from the second table. Sort merge join is typically done, and by the way, hash join is done when we've got larger data sets because it's more efficient use of memory if we can do it with a hash join. A sort merge join is done typically if one of the inputs is already sorted on the join column. So let me explain how it works. We go to the first table, we sort the data based on the join column, and then we hang on to that sorted list. We go to the second table, we sort the data on the join column, and then we grab that list, and then we merge the 2 lists together to get the result set. So the reason why this one is typically only favored if one of the inputs is already sorted on the join key is because it can be quite expensive to do sorts. Because if they don't fit in memory, where do they go? If I'm sorting a large set of data, where does it go if it doesn't fit in memory? To temp, right? Which means I'm now having to do I/O and read stuff. So it's typically done if one of the inputs is already sorted. What do I mean by that? Typically it means there's an index that starts with the join column and has all the other columns that I need. That means it's already sorted on the join column for me. They are your join methods. Now, for the nice gentleman who helped me out earlier on, there are also join types. And the special ones that I'm calling out, so the typical one that we see is the equality join, right? Is the one that we all favor. But there are other join types that show up in the execution plan. Cartesian joins, so somebody mentioned those earlier on, and outer joins. A Cartesian join, for most folks when they're doing query tuning, is somewhat of a scary join type to show up in the query. If I see a Cartesian, I start to freak out. Why? Because a Cartesian is basically take all the rows from over here and join them to all the rows over there, and it can typically explode the results set. And so it can be a little bit scary. Now, each join type requires a join method. So you'll see a hash Cartesian or a sort merge Cartesian join in this case. And it's typically selected in 2 cases. We don't think there's any rows, so the cardinality estimate is 1. Or somebody, not looking at anybody in particular, forgot to include the join condition. If your query doesn't have a join condition in it, the optimizer has no choice. It must join all the rows from this table to all the rows from that table. You with me? So a Cartesian join is chosen. The other one is an outer join, and this one's your fault too. If you write in the query an outer join, then we've got to honor that. And if you are and you're not familiar with that, an outer join basically says, I want to join these 2 tables together, but for this particular table, even though there may be no match, I still want to return all of those rows, right? So all the rows from one table and even those where there isn't a match. Typically in Oracle land, we use a little plus notation for that, but of course ANSI SQL spells it out as an outer join is typically how it's done. As I said, totes your fault that we do those because you ask us, right? So Where do I find the join types or the join methods in the execution plan? Operations, yeah. They're hanging out up here. Okay, nested loops, hash join, merge, join, Cartesian. So as I said, there's a join method and a join type in that case, because we're doing a Cartesian and we have to have some kind of method to go with it, and so we chose sort, merge, join to do that particular Cartesian product. Now, if I get the wrong join type, where do I go? Well, first of all, I don't trust you lovely people, and so the first thing I do is I look at your SQL to see whether or not somebody didn't include the join. So if you did, and we're still picking the wrong join type, I go march myself right back to the beginning of the presentation and I start looking at the cardinality estimates. Nested loops start to pop up if we really think there's very, very few rows on the left-hand side of the table, and things like that. So your turn to play the optimizer. You're armed and dangerous now. You know all your join methods and your join types. Here we go. We are joining the employees table to the departments table. We've got a where clause predicate on the department name, and we've got a join predicate on department ID. The employees table has 107 rows, department has 27, and there is a foreign key, primary key relationship between employees and department on the department ID. So that's the primary key of departments and a foreign key in the employees table. What join method are you choosing? All right, so I heard two. Show of hands. Please try and vote, even if you vote wrong. No judgment here. I may laugh, but most of the room can't see you. So, all right, who's voting nested loop? There seem to be a number of votes. Okay. Who's voting hash join? All right. Nested loops. Why? The number of rows in the tables were quite small, and I knew, because I had the primary key, foreign key, that I had an easy way to access rows in the employees table. I had an easy or quick way to access the rows in the employees table. All right. Don't worry. Time to redeem yourselves. Another go. Wow. People on this side, I'm going to have to start ignoring this whole side of the room. No. Orders and order items this time. Orders has 105 rows. Order item has 665 rows. We did remember the join condition, so it's an equality join condition. What are you going with? If I no say, there's no index. So let's show hands. Nested loop. Who's following my very brave friend back there with his hash join? Your very brave friend was indeed correct. It is a hash join. There was no indexes. So if I don't tell you, then there's no indexes. And when there's no indexes, the tables are a little larger. The hash join starts to outweigh the nested loop. All right, here we go again. Joining this time orders and employees. Orders has 105 rows. Employee has 107 rows. What are we getting? Ooh, yes, you're right. So you've guessed the join type, but I need a join method. So Cartesian, why? No join condition and no where clause specifying the join condition. Shame on this developer, but that's okay. What join method are we going to use? Merge join. I lied in this case. I know I said I'd always tell you what indexes were there. I lied. There are some indexes, which is why it picks the merge versus the hash. I did. I'm a slippery little sucker. Yeah. All right. Now, we may think Cartesian is the spawn of the devil, and most of the time it is, but there are some cases, and those of you who said you had data warehouses, this is for you guys. Oftentimes in a data warehouse, we'll have a performance layer that's in a star schema type approach, where I've got one large fact table and a bunch of smaller dimension tables surrounding that. Typically, the join conditions are always specified between the dimension and the fact table. The dimensions typically, they can, but they typically don't join to each other. It's not such a bad idea for a Cartesian product in this case even though I've got my join predicate specified, it may be cheaper to join those dimension tables together first and only go to the fact table once. Now, why would that be the case? It can be more beneficial to do that because if I join products to sales, and that's not very selective, I may end up with a giant result set, right? A lot of rows coming out of that join. Where do those rows go in between the joins? They go to memory or PGA, and if I don't have space in PGA, they go to temp, which could become very expensive to then read them back from temp, do another join, write them back out to temp before I do the final join and return the results. So sometimes you'll see a plan like this, where two of the dimension tables are actually joined together using a Cartesian product. The result of that is joined to the other dimension table, and only at the very end do we go to the sales table to pick up the rows. It may not be a bad thing if the dimension tables are very small and that resulting Cartesian product can fit into memory and no I/O is required for the query. So yes, I normally consider them the spawn of the devil, but every now and again they can be kind of useful. Yeah?
Where can you go in that explain plan where it shows that it actually does I/O? Like, is there a way to see it?
You can. It's easier though to see it in a SQL Monitor report. In the text-based plan, there isn't really a way to see it unless you do an auto trace or something like that and you look at the sessions level statistics to CIO. So in the text-based plan, not really, but in the SQL Monitor report, it would show you exactly how much IO is going on. All right, your turn, folks. Employees, full outer join to department, equality predicate on the department ID between the two. And we have, I'm getting to be honest again, we do have indexes because we've got a foreign key relationship between employees and departments. What kind of join are we getting? Yes, sir.
Full outer.
Yep.
And then hash.
Merge sorted.
Merge sorted, because you're thinking the indexes. All right, so full outer, he's definitely correct. We know our join type. The method, we've got 1 vote for hash. Who's going with him? Oh, folks, you know he's been right up until now, right? Just saying, right? But I love the faith. What about the gentleman in the front? Do we have a new leader? Are we going with the sort merge? Wow, a lot of non-voters, a lot of non-committed. People are just desperate for coffee. Hash join full outer, congratulations to our gentleman in the back. It is still correct. Last one. Sales and customer, we're joining this time. It's an equality predicate, so good developer. They've included the join method, or sorry, the join condition on the customer ID. Sales, 960 rows. Customers, 55,500 rows. Customers has a primary key created on customer ID. Sales has a foreign key created on that same customer ID. Merge Cartesian. Wow, even though I've got my equality predicate. Bold statement. Okay, anybody else? Well, we've only got a couple options. Who's going nested loops? Who's going hash? Who's going merge? Oh, not even himself now. Okay, no one going merge. And a lot of non-believers just in general. Full table scan on sales. What? Yeah, so one of the other things I told you was that the optimizer folks, as I said, they're always trying to rewrite your query. One of the things they also do is transform your queries. And what they did in this case was table elimination. It just rubbed off the customer table. Why? Because we didn't select anything from it, and because of the primary key, foreign key relationship, I knew for sure if a customer ID showed up in the sales table, then there was a primary key in the customer, and so I never, ever, ever have to go there. Number one reason why I would encourage you to put your constraints in and tell the optimizer this piece of information, because it is a smarty pants better than anybody else you know, and it will be able to do some smart stuff with your queries. Okay, we are running rapidly out of time. Some ideas about what causes you to get the wrong one. Join order is the last thing, the order in which the query, the tables are joined. One thing I just want, forget about the basic rules, one thing, or where it is. You see it through the indentation in the plan. But I don't know about you, once the plan becomes about half a page or a page, the indentation, forget about it. So I'll show you the hint that I use. I use a super easy hint. When I ask it to display the plan, I add to the format parameter plus outline. And what that will do is give me the full list of hints to reproduce that particular execution plan. The hint I'm interested in is called the leading hint. That tells me the exact order of the access of the tables in the plan. Now it uses the table aliases, so for goodness sake make use of decent aliases so you know what they are, but it will tell you the order that the join order is going in. All right, and I've given you some ideas. You've looked at an execution plan throughout this session that was actually for a query trying to find out how many of us lovely employees make more money than our boss, right? Now, I know for sure I'm not one, but anywho, that's the query, and that is the plan you've all been looking for. I have one question. Is it a good plan? So it's yes-no game show. Show of hands, and everybody in the room's got to vote. None of you slackers sitting on the sideline laughing at those getting it right or wrong. So, good plan. Bad plan? All right, bad planners, why is it a bad plan? Somebody volunteer, tell me something that gives you a hint that it might be a bad plan. Pardon? See some full table scans might make you nervous, yeah?
Full table scan and cardinality 1.
So cardinality of 1 and a full table scan could make you quite nervous, it's true. Anybody else got any ideas why it might be a bad idea? Dynamic sampling. The number one gotcha for me is right down here at the bottom of the plan. That note that says dynamic sampling for this statement level 2 means that at least one of the objects in that query does not have stats. Super nervous at this point, right? Another giveaway to me was that 1, right? The estimated number of rows being returned by the query is 1. Was it 1? Well, we didn't know. We didn't actually see the results for the query, but the estimate makes me nervous. The cost is actually reasonably low. It's only a 12, so it doesn't seem too bad. Next thing I would have looked at are those cardinality estimates correct? Nobody asked me, but that would be something I would look at. Then the join methods, as somebody said, full table scan for a 1 row, kind of interesting looking. And then I would look at the join methods. One of them being the merge join Cartesian always makes me a bit nervous. Did somebody forget a join condition? What if I told you there was a very simple fix to make this plan correct? What would it be? To gather stats, right? If you learned nothing else from me this week, let's gather stats, right? So this is what it looked like as a tree before the stats. This is what it looks like when I gathered stats. That's all I did. The cost is actually lower now than it was before. So we jumped from a 12 to an 8. The estimated number of rows returned is still 1 because that is the correct answer. There's only one smarty pants in our company who makes more money than his boss, right? Or she makes more money than her boss. Huh? Or no, yeah. But no, there is one. Cardinality estimates are a lot better now than they were. There was some that were triple digits before. Now they're all single or double digits. The join methods, look at that. Beautiful nested loops join methods. Now, and all of the table accesses are, except for departments, they're all doing index range scans followed by a table access, okay? And the join order has changed to make it more efficient. So now when I see it as a tree, doesn't that look much prettier than the previous one? Okay, so first of all, I thank you guys so much for your time. You can get a ton more information, including a white paper that goes over everything I said is available to you, and all of the slides and those links will be available to you on ODTUG's website as well. So thank you so much for your time. I'll hang around after for questions.